What's up, MITx? This is Ying Ma, your favorite teaching assistant. I'm going to give you a tutorial today on Big O notation. Now, Big O notation is a way of writing down the time complexity of an algorithm, where time complexity means basically how fast an algorithm works compared to the input size n. Right? There's also other ways of writing down how fast an algorithm is, for example, big data, but Big O is the most common way, so we're going to focus on that today. Both, by the way, Big O and big data are called asymptotic notation. So asymptotic notation refers to writing down the time complexity of an algorithm, and Big O and big data are both versions of asymptotic notation, if you will. Alright, so generally there's 6 types of time complexities, which you can read on the left hand side, and on the right hand side you can find the Big O notations. So constant time, Big O of n, Big O of 1, logarithmic time, Big O of log n, linear time, Big O of n, linearithmic time, Big O of n log n, polynomial time, Big O of n to the 2, exponential time, Big O to the 10 to the n. It doesn't have to be 10 necessarily, it could also be 2, 500, could be any number, but the n you can find here on the right side instead of on the left side, which means that this number will grow exponentially, hence the name exponential time. Now, why are we doing this topic on Big O notation? Well, some algorithms are faster than others, and what you want to have when you're writing an algorithm is preferably the fastest algorithm possible. So you want to be close to constant time or logarithmic time instead of polynomial or exponential. The faster an algorithm is, the better and the more efficient your algorithm is. Also, this topic is very important for tech interviews. So if you're going to take tech interviews for a software engineering job, the chances are likely that they're going to ask you this stuff. So it's very important to know this stuff. You'll be happy that I taught you this. So what we're going to do is go over all of these time complexities, and I'm going to give you an example algorithm for each one of them and explain to you why they have this speed, this time complexity or Big O notation. Okay? So the first one, constant time or Big O of 1. Imagine you have a number 10, which is the input, and you have a function called deduct 1, in which the number goes, the input, and basically you reduce that number by 1, and then you return it. If you would print this function, you would get this Big O of 1, and the output would be 9. So in this function there's only one step. You deduce the input by 1. Imagine if the input would be 100. So you're increasing the input by 10 times. 10 times 10 is 100. And you would run this function. Then the output would be 99. 100 minus 1 is 99. So regardless of how big the input is, there's only one operation in this function, minus 1. This number could be as big as you want or as small as you want, but there's only one single constant operation. So this algorithm right here is called constant time or Big O of 1. This is very fast, a very efficient algorithm. Now we're going to go on to a bit more complex algorithm called, which has a time complexity of Big O of log n or logarithmic time, this one. You have the same number, so the same input, 10, and you're going to input that number into a function called divide. while the number is bigger than 1, you're going to divide it by 2. So basically 10 divided by 2, divided by 2, divided by 2. You can see the output here, big O of log n. 10 divided by 2 is 5, divided by 2 in Python 2.7 is 2, rounded down, divided by 2 is 1. So you can see that with an input of 10, there are 3 steps in this algorithm, right? Imagine the number being 100. How many steps would there be? Let's run this. Okay, so big O of log n, yeah? 100 divided by 2 is 50, divided by 2 is 25, 12, 6, 3, and again, rounded down, becomes 1. And you can see that there's 6 steps here. But hold on, this is quite strange, isn't it? The initial number was 10. For an input of 10, we had 3 steps. 10 became 5, became 2, became 1. But now we increased the number tenfold, from 10 to 100. So the input is 100 times as big. But the amount of steps that it takes for this algorithm to complete only became 3 bigger, right? So when you have an algorithm that divides the input by 2, or by 3, or by 4, or by any of those numbers, it's called logarithmic time. Yeah? So compared to the input, this algorithm has a speed of big O of log n. Now it might still be a bit difficult to comprehend for you, but once we move on to the next algorithm, linear time, you will start getting a better picture of how time complexity works. So let's go on to this one. Big O of n, linear time. Again, input 10, and this function is going to add ones to a test list, right? This function is going to create a test list that's empty. And for I in range 0 to num, so 0 to 10, this for loop is going to loop 10 times. Test list.append 1, so you're going to append the integer 1 to the test list 10 times. And every time you append 1 to the list, we're going to print it. And the output would be this. Big O of n, linear time, 1, 1, 1, 1, 1, 1, etc., etc. And if you count, you'll see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. The input was also 10, right? Because for every number, for every input, you're going to make one extra loop and add one extra 1 to the list. If number would be 10, if the number wouldn't be 10 but would be 100, you would have 100 steps, because you will add 100 ones to the list, right? So this is linear time. So input 10, 10 steps. Now compare this 10 steps to the previous one. When the input became 100, from 10 to 100, you only had 3 extra steps. In linear time, you would have 90 extra steps. So this O log n is much more efficient, much more efficient than big O of n, linear time. So you want to have this one. So let's go on to the next one. Big O of n log n, otherwise called linearithmic time, because it's a combination of linear and logarithmic, hence linearithmic. We're going to have a test list of 10 elements. And again, I chose the number 10 so you can compare the different algorithms with the same input. So test list 10 elements. And we're going to have a function merge sort. So merge sort, I'm not going to go over all of the code in this algorithm, but what you need to understand is what this algorithm does is it's going to take this unordered list, and because the numbers are not ordered, you have 1, 43, 31, it's not ordered, and this function is going to order the list. and it's going to do it in 2 steps. First, it's going to take these 10 elements and divide them by 2. So you have 5 elements on the left side and 5 elements on the right side. And then it's going to divide those elements on the left side again into 2. And the elements on the right side the same way. So you're going to have this list, then you're going to have this list, and you're going to have this list. And then again, this list is going to be divided into 2, and this one also. Does this sound familiar, these operations? 10 elements divided by 2, divided by 2, divided by 2. That's logarithmic time, right? That's big O of log n, right? Once you divide all these elements into single elements, you're going to compare elements to each other, and if what you're going to do is you're going to take the smallest element and put it on the left side, and the bigger element you're going to put on the right side. So 143. Here you're going to put 6 first and then 21. Then you're going to compare with 31. You're going to add 31 to the end of that list. Then you're going to compare this list with this list, and you're going to have 1, 6, 31, 31, 43. And then you're going to do the same on the right side. So what that basically means is you're going to compare every element to each other, all single elements, and then append them to a new list in sorted order. What does that mean? It means that every element in this list is going to be appended to a new list. So every element will be appended to a new list. What does that mean? It sounds familiar, right? It's linear time, because every element is going to be appended at some point. So that's big O of n. So because in this function you're going to have both log n, the dividing into 2, and the big O of n, the linear time, the appending to a new list. Functions like this are called linearithmic time. So big O of n log n. If you print this function, the output will look like this: left list, right list, comparison, and then appending to a new list, 143, 21, 6, first 6 and then 21, all the way through the list until you have a sorted list that you can see here, 1, 5, 6, 13, 21, etc. So big O of n log n. And compare the amount of steps. I didn't count them myself, but it looks like about 30 steps with an input of 10. In the past, time complexity, when you have had an input of 10, you would have 10 steps. Now you have 30 steps. So this big O of n log n is less efficient than this one, linear time. Big O of n. Make sense? Next we have another function which is polynomial time, big O of n to the 2. Again, you have a test list of 10 elements, unsorted, the same list actually, and we're gonna pass them into a function called bubble sort. What bubble sort does is there's a loop that goes through all of the elements. And there's another loop that goes through all of the elements, and you compare the numbers next to each other, and if the number to the right is smaller than the number to the left, you're going to swap them. Here, swap, and every time that happens, we're going to print a list. So every step is going to be printed. So first, the first loop would iterate over 1, and then compare 1 to 43, 31, compared to 21, compared to 6, all the way to the end. Then there's going to be a loop through 43, and this number is going to be compared to 31, 31, 6, 96, etc. Then 31 is going to be compared to 21, 6, 96, etc. That's a whole lot of steps. Hence, big O of n to the 2. The result of this algorithm will look like this. You can pause the video and check out yourself how it works internally. So you can see some numbers being swapped here. 43, 31 is being swapped here. And all the way in the end, you have a sorted list. 1, 5, 6, 13, 21, etc. Same as the last algorithm. But this one takes many more steps. Can you see that? There was a whole lot of steps. Compare that with the last algorithm. That's only 30 steps. This one has like 60 or 50 steps. Generally, if you have an algorithm and you have a nested for loop, so a for loop within a for loop, the algorithm is going to be big O of n to the 2. This is not a very efficient algorithm. If you can write the same function with a faster algorithm, for example, n log n, big O of n log n, you should do it, because it'll take less steps and it'll take up less of your computer's processing power. Because it's a better algorithm, it's more efficient. It's big O n log n. Now lastly, the most inefficient algorithm would be exponential. So big O 10 to the n. It doesn't have to be 10, it could also be 2, it could be 500 to the n. But imagine if n is 10 and the first number is 500. You would have 500 times 500 times 500. I mean, that number would grow really fast. So you can understand that it's a very inefficient algorithm. I didn't write an algorithm for this one because it might be a bit complex. But what I did do is give you an example of a certain problem that would require exponential time. So let's say you have a password consisting of numbers, and the password has 2 numbers, and you want to test all possible combinations. How many combinations would you have? Well, every number has 10 possibilities, right? From 0 to 9. And if there's 2 numbers, you would have 10 times 10 possibilities, which would be 100 possibilities. Now let's say the password has 6 numbers. In that case, you would have 10 to the 6. 10 times 10 times 10 times 10 times 10 times 10. 1 million possibilities. 1 million. If n is 6, you would have 1 million possibilities. So 1 million steps, 1 million operations in your algorithm. That's how inefficient this algorithm would be. And so you want to avoid exponential time. You also want to avoid polynomial time. Basically, the higher up you go into this list, the better. So constant time is the best. The worst is exponential time, which means that your algorithm is really bad. To illustrate this, let's look at this function. 10 times n to the 2 plus 10 times n plus 20. Let's say this represents an algorithm, and you'll notice that there's 3 parts in this algorithm. There's 10 times n to the 2, there's 10 times n, and there's 20, yeah? Imagine the n is 1000. The output to this function would be 10,010,020. Now if you look at the 3 parts of this function, the 20 is not going to have a big impact on that output number, because it's only 20. It's more than 10 million steps in this function. 1000 times 10 would be 10,000. Also 10,000 doesn't matter that much for this number, because 10 million is much bigger. And this part of the algorithm of the function is basically what's going to be responsible for this big number. So if this would be an algorithm in a big O notation, you would only write the big O notation down for the slowest part of the function. The part of the function that has the biggest impact on how fast an algorithm is. So this function would be not constant time or linear time, but polynomial time. So this function would be big O n to the 2. Yeah? I can illustrate that for you in this graph that I found online. On the x-axis, you can find the number of inputs from 0 to 10. And on the y-axis, you can find the amount of time it takes from 0 to 50. And let's say the input would be 4. If you had logarithmic time, it wouldn't take that much time, right? Maybe 1. Let's say these are seconds. 1 second. Linear time would maybe take 4 seconds. Log linear or linearithmic, like we learned it in this tutorial, maybe takes 5 seconds. Quadratic, which is similar as polynomial, takes 15 seconds. Cubic is basically n to the 3, so not n to the 2, which is quadratic. Cubic would take much longer, and exponential, I mean, you can't even see it. It would take so much time. Like, remember the password example? There would be so many steps. So if you write an algorithm, you want to stick to the logarithmic and linear time, or log linear, or constant. So I think that's about it. Again, go through the examples and try to really understand this topic. It's very important. If you're going to have a tech interview, there's a big chance that they'll ask you about this kind of stuff. And, well, as a teaching assistant, I just want you guys to succeed and get a good job as a software engineer. So, you know, thanks for listening. Keep programming, and see you guys later. MITx, baby.